Oh, okay, don't forget to do your corrections by midnight tonight. Go ahead and post those. Just take a picture or PDF file. I found it on a lot of phones, like iPhones, particularly if you do it in notes, it'll automatically turn it into a PDF. Google, I think it has the same function. I mean, the other phones have the same function. It's under, I want to say notes also. It's also called notes. It'll take a PDF, and so that makes it easier. And you can take multiple pages and just upload it as one file if you want. So, okay. So in chapter 4, we learned that most reactions fall under 4 categories. We have substitution reactions, SN1, SN2. We have addition reactions, hydrogenation. We have elimination reactions, E1, E2. And we have rearrangements, carbocations. Okay, so we've actually attacked all of these things right now. Okay, but now chapter 8, we are going to look at a whole bunch of different addition reactions. Okay, now we found out in the substitution reactions, we can have regioselectivity and stereoselectivity, or not, if it's a carbocation. In elimination reactions, we have regioselectivity and stereoselectivity because of how the we have to be anti-periplanar to do the elimination. Okay, and in rearrangements, we found we're going to only go to the most stable, and we have 3 ways to do that, which is 1,2 hydride shift, 1,2 methyl shift, and ring expansion. Okay, so there's an order to things. We need to keep those track of those order. Okay, now in the addition reactions we're going to do today, we have regioselectivity, but not necessary, and some stereoselective. But you have to remember that the double bond can react on the top or the bottom. Now, in the addition reactions we learned with hydrogenation, we had 2 kinds of reactions. We had a Syn addition, meaning they were adding on the same side, which gave a rise to certain products. And then we had a trans addition, where we can do, or an anti-addition, where they're adding on the 2 different sides. This is important for your reaction table. You need to put whether these are Syn addition or anti-addition on your reaction table. Okay. Now, off to chapter 8, which should be that one. All right. So now we're going to talk about addition reactions to alkenes and alkynes. So it's all about taking our pi cloud and turning it into sigma bonds. Okay, we're taking our pi bond, turning it into a sigma bond. So we're going to change hybridization every single time we do an addition. Now, we can do 1 addition or 2 additions to alkynes, but they'll follow the exact same rules that we got for the alkenes. Okay, so it's just stepwise. We'll do one and then the other. Okay, but it's exactly the same rules. So we don't have to worry about, oh, no, it's an alkyne. No, it's going to follow the same rules. Okay, so the general form of an addition reaction is we have something has a pi bond, and there's going to be something that's going to be partially positive or positive, something that's going to be partially negative or negative, and they're going to add selectively across our double bond. Okay, so that's what we're looking for here. Alkenes are electron rich, which means that our partially positive thing is going to be the thing that's doing the attack. So what's a positive or partially positive thing? It's an electrophile, meaning our alkene is our nucleophile or our Lewis base. Okay, so we're having an electrophile react with a nucleophile. So that's one of those 5 things that can happen in a mechanism. Okay, so when we look at this, we have to say, okay, they can either attack on the same side of the double bond, like maybe they don't break apart until they're actually forming those sigma bonds with the carbon, or we can add anti, meaning one adds on one side and then one comes around the other side. So that means that those have broken apart and they're adding on 2 different sides. Okay, so but we still lose our double bond and we gain 2 sigma bonds. Okay, so, all right, lecture's done. Just memorize this table. No, I'm kidding. These are all the different types of reactions I'm going to cover in this chapter. So, starting from an alkene, and again, we like cyclohexene, so you know what's happening. This makes it easy to tell us whether it's a syn or anti-addition, because the products are going to either be cis or trans, depending on how the ring is, right? So that's why we use cyclohexene as a basis for all of our reactions here, because then we know whether it's syn or anti-addition. The first thing we have to do is we have to say, oh, you know, we took away an acid to make the alkene. Well, we can add acid across that double bond. And that can be syn and anti, okay? Depending on which way we do it. If we can add water across, because dehydration is one of the ways we make an alkene, we can go back the other way. So excess water and a drop of acid will give us hydration, and that goes syn and anti. Now, why? It's all about the mechanism. So in your book, the last page of the chapter has images of the transition state. I would go to that book and look at those transition states, because that's going to tell you whether it's a syn or anti-addition. Okay, it's the last page in chapter 8. Okay, now we have halogenation. We're going to add 2 halogens, 2 single bonds to halogens, and it's always anti because of the mechanism. We can also do that with a halogen and water, and we end up with a halogen and a hydroxide. The way we do this is we just have a whole bunch of water around, and it acts as a nucleophile or a Lewis phase. The other thing we have here is the hydroboronation. Hydroboronation oxidation. So what we end up doing is we add boron across the double bond. And then we oxidize it off, forming an OH group. Let me pause for a minute. Resume recording. In the boronation, we're going to add boron and the hydrogen across the same side of the bond, so it's syn addition, but then we oxidize off the boron to give us an OH group. In oxymercuration-demercuration, it's a slightly different mechanism, and it has different regioselectivity. Okay, so we have regioselectivity for the halohydrin reaction. We have regioselectivity for the hydroboronation, and we have regioselectivity for the oxymercuration-demercuration. Now, why is this important? Because one's going to give us primaries and primary alcohols, one's going to have secondary alcohols, and actually the reaction up here might give us tertiary alcohols. So it's selective to what type of alcohol you want to make, which is something you need to put on your reaction table. Okay, because when we do multi-step synthesis, you're going to want a primary, secondary, or tertiary alcohol. Okay, so the other thing we can do is we can make a diol right here. And this is syn addition, and I want to show you the intermediate of this, shows you why it's syn addition. We can also go ahead and just rip the damn thing apart. Sorry, excuse my language. We can just break that double bond and turn it into ketones or aldehydes. And then we can also do what we already did in the last chapter, hydrogenation. And we learned that hydrogenation is syn addition because it sets down on the surface and adds both at the same time. All right, so these are all the reactions we're going to learn in this chapter, plus a couple more. But the key here is we need to know whether they are, what their selectivity is. Each of these reactions we want to use selectively because it gives us a certain product. So look for that in our mechanisms. Okay, so the first mechanism we want to talk about is halohydrogenation, meaning we're going to add acid across a double bond. Okay, and we have a rule for this. Is that the acid's going to add across the double bond, and it's going to do it, well, let's see. Our alkene is a nucleophile because it has electrons, right? Which means the hydrogen is the partially positive part of the acid, which means the hydrogen is going to bond first. So we're going to have our electrons from our double bond come up here to the hydrogen. The electrons that form the sigma bond between the hydrogen and the bromine go up to the bromine, turning our bromine into the new nucleophile. Okay, so not once a nucleophile, always a nucleophile. It changes based on your electronic structure. So now this is no longer a nucleophile. It's now an electrophile because it has a positive charge on carbon, because it used the electrons to form the bond, a sigma bond with hydrogen. So that means a carbocation is our intermediate here. What's the problem with carbocations? They rearrange. So that's a problem. But what's the other good thing about carbocations? No, the good thing about carbocations is we always know they're going to form the most substituted carbocation possible, right? So if you're forming the most substituted carbocation, that means your hydrogen's always going to go on the side with the fewer substitutions. Your halogen's going to go on the side with more substitutions. We have a rule for that, and I'll get to that in a minute. Okay, so this is our slow step, forming our carbocation. And then once our carbocation forms, this is very fast because we have a good nucleophile and we have a positive charge. Boom. Pops on there really fast. So we have two successive Lewis acid-base reactions. Base, acid, acid, base. Notice they've switched positions when they do it. Okay, so this is number 3 on our list of things that can happen in a reaction. Okay, so what is the reaction diagram? Well, if we're forming a carbocation, we are forming an intermediate. Therefore, our reaction coordinate diagram says we form an intermediate. We have our slow step, which is our highest activation energy, our fast step, which are the lowest activation energy, and usually we end up with a exothermic reaction. Wow. Sigma bonds are more stable than double bonds. Sigma bonds are more stable than pi bonds. Okay. So usually it's exothermic. Now, I said that carbocations are good and bad. Right? The good part about carbocations is we know we're always going to put it on the more substituted side, right? Because it's more stable. So that leads to Markovnikov's rule. In Markovnikov's rule, when you add the hydrogen across the double bond, it is going to go to the less substituted side because you're forming the more stable carbocation. It's not a mystery, okay? So Markovnikov's rule says the electrophile, usually the hydrogen, at least in the hydrohalogenation, is going to go to the one with the more hydrogens on it. So in this case here, this is propene, okay? So are we going to go to carbon 1 or carbon 2? Carbon 1, because there are 2 hydrogens on carbon 1, there's only 1 hydrogen on carbon 2. Hydrogens can't stabilize a carbocation. Carbon can help stabilize. So that means that our hydrogen is always going to add to the more substituted side. So this doesn't happen. We don't put the chlorine on that position, that number 1 carbon. We only put the chlorine on the number 2 carbon, because that number 2 carbon has 2 carbons attached to it. Carbon 1 only has 1 carbon attached to it. If it only has 1 carbon, you're going to add the hydrogen to that. So the actual, in a southernism, you would say them that has gets. So if it already has hydrogens, the more hydrogens it has, it gets the hydrogens. Okay, but the reason is carbocation stability. So it's not a mystery, it's exactly the right rule. Okay, so Markovnikov's rule says that we are going to add the hydrogen to the less substituted carbon. We're going to add the halogen or other nucleophile to the more substituted carbon. Okay, does that make sense? I think it makes sense because it's, it follows all the rules we've already learned. It doesn't break any rules, right? Okay, so it's all about carbocation stability. So if we're trying to form the primary carbocation, that's going to be much higher in energy, a much higher transition state to get to, and therefore we're going to hit this one first. In theory, the difference in this energy is actually so great, you hardly ever see the substitution at the other side. I mean, it'll be like 99.9 to 0.1. You never have enough energy to form that primary carbocation. And therefore, you always end up with the more stable carbocation here, and you end up with a stable product. Okay, so that leads us to the regioselectivity. Tells you that hydrogen's going to go on the more hydrogenated side, and the halogen's going to go on the more substituted side. But there's also stereochemistry involved because we form a carbocation. And what do we learn about SN1 reactions? You're going to get a 50-50 mixture of R and S because you formed a carbocation. Okay, so it follows the SN1 reaction because we followed a carbocation, and the same rule applies. Okay, so that being said, let's move on to the addition of water to an alkene. Okay, so in this, we typically use an acid-catalyzed, being like a hydronium ion, as the electrophile, and our double bond is our nucleophile, right? Is that right? This has the electrons. So that makes this the electrophile and makes the hydronium ion or the hydrogen the electrophile, right? It's partially positive. This has excess, this has extra electrons. This is partially positive. So this is our electrophile. This is our nucleophile. So alkenes are nucleophiles. All right. So what's going to happen here is we're going to do the same thing. We're going to form a carbocation because we're going to transfer a proton. We're going to use those 2 electrons from the double bond to form a new sigma bond. And that gives us a carbocation, which means it's a Markovnikov's rule applies. Forming a carbocation, therefore, the more hydrogenated side gets hydrogen, the more substituted side gets the OH. Okay, so that means we're only going to get secondary and tertiary alcohols out of this reaction. We can't get a primary alcohol out of this reaction because we can't form the primary carbocation. Okay, so we can have carbocation rearrangement. So you can actually have the alcohol not be where the alkene was, but actually move over 1 carbon, only 1. 1, 2, either 1, 2 shift by a hydrogen or a methyl group or a ring expansion. Okay, so this is typically acid catalyzed. The reason is you get your acid back at the end. Now, if you don't use water and you use an alcohol instead, you still have to use an acid catalyst. But because you're using an alcohol, it already has 1 carbon-oxygen bond, and you form an ether. So this acid-catalyzed hydration actually can form alcohols and ethers. Okay, we were able to form alcohols and ethers using SN1 and SN2, but this is a different reaction where we're actually adding across a double bond, forming carbocation, which might rearrange, and then we can form alcohols or ethers. All right, so what's the mechanism? Well, the first step in the mechanism is you have to protonate either the alcohol or the water. Okay, so in this case here, we've protonated water and we turned it into the hydronium ion. The hydronium now has a positive charge. So it is now an electrophile. We have electrons in our double bond, so it's the nucleophile. So what we're going to do is we're going to add that hydrogen to there with these 2 electrons from the double bond to give us a new sigma bond and the most stable carbocation possible. In this case here, we're actually forming a tertiary carbocation, so it doesn't rearrange. And then the next step is a fast step. We have water, which we generated because we transferred a proton. We have water now acting as a Lewis base, forming using its lone pair of electrons to make a new sigma bond with the carbon that's partially positive, and then we get this protonated alcohol. Okay. So now we have to lose a proton to generate our neutral alcohol and regenerate our acid. So it's acid catalyzed. So let's look at this here. Nucleophile, electrophile, nucleophile. This is an electrophile. This is a nucleophile. These are both, well, this is an electrophile and this is a nucleophile. So you can follow every reaction and notice they change parts. That's fine. Where are the electrons? That's going to tell you where. Okay. Questions about the mechanism of hydration. This is very similar to the hydrohalogenation, right? Because we form a carbocation and we have in one case, we have the lone pairs from the halogen creating a new single bond. In this case, we have the lone pairs from the oxygen forming a new bond. So it's the same mechanism. It's just what is the nucleophile. All right. So oxymercurization, demercurization is a little bit different. Technically, it is a Markovnikov addition, meaning we're going to put the hydrogen on the least substituted side. We're going to put the OH on the more substituted side. But the benefit of the oxymercurization, demercurization is it doesn't rearrange because it doesn't form a carbocation. Different mechanism, meaning you can get secondary alcohols where your hydration might rearrange and give you a tertiary alcohol. So we can get selectively secondary alcohols with the oxymercurization. And we get a mixture of syn and anti, which is kind of weird because you actually kind of add it across the double bond at one time, but oxidizing off the mercury, you can actually get a mixture of them. The great thing is we don't need acid. We don't have rearrangements. It happens very quickly. Downside is mercury is toxic to humans. Actually, some animals use mercury as their oxygenating agent, believe it or not. There's even a slug in the ocean that uses vanadium. Vanadium in their blood is purple. Anyway, there's also one that uses copper and their blood is green, but that's another thing. Okay, but it's toxic to humans, but it's very selective. It does not rearrange. That's the benefit of this reaction. Okay, so we're going to see here is we first have to add our mercury to it, which then gives us our hydrogen going on the more substituted side. And then we have to reduce off the mercury to get to our alcohol or our ether. Again, we can use exactly the same reaction with alcohol and with water, one to form ethers, one to form, just like the hydration reaction, we can form ethers or alcohols. All right, so what's the mechanism? Oh, well, the mechanism in the book is actually wrong, so I wouldn't worry about the mechanism. But the idea here is that you add mercury across the mercury is on this one right here. The hydrogen's on this one right here, and then we reduce off the mercury, giving us the alcohol. All right, the next one is also selective. This is called the hydroboration oxidation reaction. So in this case, the boron adds to the least substituted side. But wait, Markovnikov says that the hydrogen goes to the more substituted side. Well, in the case of the carbon-hydrogen bond, the hydrogen is less electronegative. But boron is actually less electronegative than hydrogen. So our less electronegative atom is actually adding to the less substituted carbon. So in this case here, we are technically breaking Markovnikov's rule. So you want to either call this anti-Markovnikov's or selective to form primaries. Okay. So the idea is you add the hydrogen and boron across the double bond. Once you do that, then you have to oxidize off your boron to give you your alcohol. This is the only way to get to a primary alcohol. Oxymercurization, demercurization can get secondary or tertiary alcohol. This is the only way to get to a primary alcohol. Okay. And it's syn addition. And if you look at the book on that last page, you'll see why. Okay. Okay. So I want to actually pull up the book here. Finder. And solids. All right, I'm going to stop sharing and reshare. And I want to pull up the last page of chapter 8. Oops. And plus, plus, plus. Okay, wait, that was it. And rotate. Clockwise. All right. So this is where you need to go and look at this. Now, the reason I think this is very valuable is put it in your reaction table, but it also gives you a visualization of why it does what it does. The first reaction here is the hydrohalogenation or the hydration reaction. They go through the same intermediate, carbocation. It's going to add a hydrogen to the least substituted side, and it forms the more substituted carbocation. So it gives the same intermediate. Now, in halogenation, which we haven't done yet, oxymercuration, demercuration, we end up with this right here. Okay, now this intermediate's a little different because the mercury sits on top of the double bond. Okay, and that means that it's going to have one bond that's going to be longer than the other. The one that has the carbon that can make a more positive carbocation, the one that's more substituted, is going to be longer. That means our water, which is our nucleophile here, is going to attack this side. So that's why it gives us a secondary alcohol, but it doesn't form a full carbocation, so it doesn't rearrange. That's why this intermediate is very important. Now, in hydroboration oxidation here, we have the hydrogen and boron adding across the double bond at the same time. But boron is less electronegative than hydrogen. Therefore, it's going to add to the less substituted side. And then when we oxidize this off, we end up getting our alcohol. So these, I believe, I'm very visual in this. I love this because if I remember this, I never get the answer wrong. Because it's like, oh, that's the intermediate, so it has to be this way. So argue it through yourself to see if those can be done that way. All right, so let me go ahead and, there we go. Switch back to my iPad and continue. Okay, so come on. All right, so that means that we have selectivity now. We can make a tertiary alcohol, we can make a primary alcohol, we can make a secondary alcohol by choosing our reagent. This is important for your reaction group. Okay, so in the case of the acid-catalyzed hydrogenation, you're only going to get second and tertiary alcohols because you form a carbocation and it can rearrange. So you might not even get the alcohol where you started your alkene with. So there's going to be some problems with that, and you'll see that. In the oxymercurization-demercurization, you're only going to get the alcohol on one of the carbons of that alkene. It's not going to rearrange because there's no carbocation. In hydroboration oxidation, you're only going to get on the least substituted side. So what does that mean? That means you can start with the same starting material and you get a tertiary, a secondary, or a primary by choosing your reagent. Your reagent is so important here. So let's look at this little alkene right here. It's got an isopropyl, so it's an isobutylene. Actually, it's propylene, methylpropylene. But what we have here is in the hydration with acid, it's going to start with a carbocation here, but then it's going to move here by a 1,2 hydride shift, and you get a tertiary alcohol. Okay, so we see that we're going to get our carbocation is going to be here, and then that's going to rearrange here to give us our tertiary alcohol. But when we do the oxymercurization-demercurization, our intermediate is a little different because our intermediate has, we lose the double bond here and we add mercury here. And then because this is the more substituted side, this is partially positive, this is partially negative, and we have our OH come in and react with it on this side. And then once we have that, we end up with our other intermediate where we have OH is now bonded to that more substituted carbon, but it didn't rearrange because it never formed the carbocation. And we have our mercury over here, and then that gets broken off by our reducing agent. We get a hydrogen where the mercury was. I misspoke earlier. You get a hydrogen where the mercury was, meaning you have a secondary right here. And then selectivity wise, we can go for the hydroboration, which our intermediate is boron right here. Oops, that's a with 2 hydrogens on it. And our first hydrogen is added here. Again, boron is less electronegative than hydrogen, therefore it follows Markovnikov-Rule chemical. But if you think about it as anti-Markovnikov, that's fine. Just write it down in your reaction table. But then we have to oxidize this off. And when we oxidize that off, that's where we get the OH. When we oxidize the boron off. And therefore we get a primary alcohol. Same substrate, 3 different reagents, 3 different products. This is where things start to get a little harder. You got to start paying attention to regioselectivity in our reactions as we move forward. Okay. In fact, at the end of this chapter, we're going to do what we call multi-step synthesis or retrosynthesis or retrosynthesis. All right. So the next reaction we're going to look at is hydrohalogenation. So the first 3 reactions we saw gave us alcohols. Okay. This reaction is going to give us a dihalide, and it's always going to give us a bisotyl dihalide. Carbon 1, carbon 2 of the double bond end up with 1 halogen on each. Okay. So the mechanism's a little different than everything we've done before, and it'll work with chlorine or bromine. Turns out iodine is not reactive enough, and fluorine just blows up. It's just really too reactive. So this is best for chlorine and bromine. Okay. Notice that we do it dark, room temperature, and in a solvent called carbon tetrachloride. Carbon tetrachloride does not participate in the reaction. It's just a solvent that can't be halogenated. It already has halogens. So you'll always see this number, and then it's also a non-polar solvent, right? Because all the dipoles cancel out. So why dark? We're going to learn about that in chapter 10. If you do it in the light, it might form a radical. And that's chapter 10. So we're going to avoid chapter 10 right now and just say it's in the dark. Okay. So room temperature in the dark, you can heat it up a little bit if it's chlorine, but you don't have to. The halogens add across the double bond because the bond of the halogen is polarizable. Okay. They have, full octets, but that is a polarizable bond. Now, the proof that we have a different mechanism is that we do not rearrange, and we only get anti-addition. Do not rearrange, and only get anti-addition. So there's no carbocation formed. If there was a carbocation, we'd have a mixture of syn and anti. Go back to that first slide where we had syn and anti. Okay. So what's the mechanism? So the mechanism has our electrons from our double bond help polarize the halogen, the dihalide right here. And so two of the electrons from the double bond reach out and grab the halide. Two of the electrons from the halide reach out and grab the other carbon because we don't want it to form a carbocation. And we end up with this bridged polonium anion. Okay. This intermediate is very important, this bridged intermediate, because if you have a bridged intermediate like this, can the other halogen attack from the top? No, it can only attack from the bottom, ergo, it has to be a anti-addition. It has to be anti-addition because the top is already blocked. We have to come from the bottom. So now that we have this partially positive, this actually it's a full, full charge, full positive charge here. We can have attack by our nucleophile, which is our other halogen here. Now, is this reaction regioselective? We don't know, because in theory, the nucleophile should attack the more substituted side, but you have a halogen on both carbons and you have a sigma bond which rotates. But we do know it's an anti-addition reaction. Okay, so let's look at the stereochemistry. To prove to ourselves it's an anti-addition, we're going to use a ring because we don't have that free rotation. So if we have our reaction here and we attack from the top, we're going to get an intermediate where the halogen is on the top. Turns out that is a chiral because we don't have 4 different things attached to any carbon. So, and then when we have attack by our chloride ion, it has to attack from the bottom because the top is blocked. And therefore it can attack this side or that side. Doesn't matter. No matter what we do, we end up with our trans product. Okay. One attack to the top, one attack to the bottom, always get a trans product. Therefore, it's an anti-addition. Make sure you write anti-addition on your reaction table. Okay, so then what if it attacked from the bottom? Well, it can attack from the top or the bottom. It doesn't matter, right? Because it's pi bond, it's on the top and bottom. So what you're going to end up with is it'll attack from the bottom. But guess what? You flip this over 180 degrees. It's exactly the same. So when we have attack by our chloride ion, we end up again with our trans product. But we now have an anti because they're non-superimposable mirror images of each other. So we have regioselectivity, we have anti-addition, but because you can attack from the top or bottom, if it's fixed in space, you have an anti. In fact, you have a 50-50 mixture, a racemic mixture of an anti. Questions on that? Most important thing about this is that triangular intermediate, that halonium ion, the bromonium or the chlorinium ion. That is the most important thing because that tells you it has to come from the other side. All right. So let's look at stereochemistry on something that can rotate. So the cis-butene is fixed in space, right? We do not rotate around a double bond because the pi is blocking it from rotation. So let's say we take our cis-butene and we attack it with bromine. Okay, so that means we're going to get anti-addition, but we're going to get anti-addition where bromine is on one carbon that was on the top, and bromine is on one carbon that was on the top. Okay, and so the one attached on the bottom are two different things. Now, because we have four different things on each of those carbons, we have possibility of diastereomers, but these happen to be enantiomers because we have non-superimposable mirror images. We can rotate this bromine around and do all the kind of funny stuff, but we also don't have a mirror plane. You rotate this bromine up, the hydrogen goes back, the methyl group goes forward, no mirror plane. Now, what if we don't take the cis isomer, we take the trans isomer? We're going to form the triangular thing on the top, and it has to attack from the bottom. It can attack one, carbon 1 or carbon 2, it doesn't matter. So we're going to end up with a carbon 1 on this one, or carbon 2 on this one. But what if we rotate this around? The methyl group goes back, the hydrogen comes out, and we have a mirror plane. Okay, so you have to look at this. So if I asked you to, what are the products of the cis-butene, you're going to draw them, and you're going to look for a mirror plane. If you don't have a mirror plane, leave both of the compounds there. I'm going to say, hey, do it for the trans one. And you're going to draw both of them, and you're going to look for a mirror plane. You're going to say, oh, there's a mirror plane. Cross that one, because it's a meso compound. Okay, so we're moving chapter 5. Chapter 5, stereochemistry. Questions on this? All right. So what happens if halogens are not your only nucleophile? Let's say we run the reaction in water instead. Why? Well, water is not halogenatable, so it's called carbon tetrachloride, and it can act as a Lewis base. It can act as a nucleophile. So if we form that bromonium cation or that chloronium cation, we now have an opportunity to be attacked by any nucleophile. If you're using water as the solvent, there's so much more water than bromine ion that it's going to react. And we have what we call the halohydrin reaction. The halogen has to react first to form this intermediate. But now our water can act as a nucleophile, or we can even have an alcohol. If we run the reaction in an alcohol, you can form an ether. But most of the time we call this the halohydrin reaction because it makes a halogen on carbon 1 and an alcohol on carbon 2, or the alpha carbon and the beta carbon. Okay, so this is cool because now you have not one functional group, but now you have two functional groups of different kinds. So you can use the alcohol in some reactions, you can use the halogen in other reactions. So it's a very useful reaction. Okay, so you can use water, hydroxide, alcohol, or even another halogen. If you have a whole bunch of another halogen in there, you can get a bromochloro compound. And it's the same mechanism. You have to form your polonium cation first, and then you just have to have a whole bunch of any nucleophile. And you can do that. All right. So the most common one, though, is water. We call it the halohydrin because hydrin is your OH group that you can have. So let's look at the stereochemistry. It's always anti-addition. Why? We're blocking the top with the bromonium or the chlorinium. So it's always going to be an anti-addition. You're always going to have trans isomers or the like. And in addition to that, your OH group is always going to substitute the more substituted side. Write that down. This is important. Because this carbon in the intermediate here is more positive than this carbon. Why? Doesn't form a carbocation, but it forms the same reason as carbocations. The more substituted carbon is going to be more positive than less substituted carbon. So if the more substituted carbon is going to be more positive, that means our second attack is going to attack at the more substituted carbon, meaning we're going to end up with the halogen on the less substituted carbon, the OH or the ether or the chloride is going to end up on the more substituted carbon. It's all about the mechanism. It's all about stability. Okay. Not a mystery. So you're going to want to write down the regioselectivity of this, meaning your OH is going to be on the more substituted carbon, your halogen is going to be on the less substituted carbon on your reaction table. Okay. All right. So this is kind of describing why. If you have this carbon here, you're going to have a polarized bond between the carbon and the bromonium cation. And you're going to have a polarized bond here. But of the two carbons, only the one that's more substituted can support more of that positive charge, meaning it's more electrophilic, meaning it's more likely it's attracting the nucleophile. So the nucleophile is going to attack on the more substituted carbon, lose a proton, and get to the more substituted alcohol, and the halogen is going to be the least substituted side. That makes sense, right? Because it's following the same rules of carbocation stability, but we don't form a carbocation. All right. So let's change gears a little bit. Okay. The cool thing about the last reaction is we now have two functional groups. We have a halogen and an alcohol. Okay. But what if we want two alcohols right next to each other? We can't do that with just water and acid because we're going to transfer a hydrogen first and an OH second. So we're not going to get a diol, two alcohols, without some other reagent. So the reagent of choice here is osmium tetroxide. So it's osmium with 4 oxygens on it, and 2 of those oxygens are going to transfer. Okay. Now, the really cool thing about osmium tetroxide is it forms this intermediate here. This is called an osmate ester. Okay. This osmate ester does Syn addition because it's forming this 5-membered intermediate on one side of the ring. So it always does a Syn addition, always forms the osmate ester. And then you can take this right here and reduce off this bond here, leaving this with 2 alcohols. Again, Syn addition. So we have a 1,2 diol, and they're both on the same side of the ring. Okay. Now, the only downside to osmium tetroxide is it's also very toxic to humans. And so what they've figured out is that they can use a reagent that oxidizes the osmium dioxide to osmium tetroxide in solution. And we use that using this oxidized nitrogen material here. And we call that N-morpholine. Morpholine is this right here. The N is where the methyl group is. So the methyl group is on the nitrogen. And the oxide, there's an oxide on the N. And so you can put 2 equivalents of this will oxidize the osmium back down to osmium tetroxide. So you just need to use a pinch. So you can use catalytic osmium tetroxide as long as you have molar equivalents of this. But key things are the osmate intermediate which is on the last page of the book, and the fact that it's Syn addition. And it's the great way to make diols. We have another reaction that we can make a diol where we change the reagent to potassium permanganate, but we have to be very careful because potassium permanganate, if you heat it up, it's going to blow the reaction apart. It's going to break apart the double bond. But if you do it cold and dilute, you can get the same kind of intermediate, and it forms the same intermediate and does the same cis addition. And that reaction's in the book. Okay, so let's summarize everything we have here. So we have a mixture of Syn and anti with hydrohalogenation because we form a carbocation. We have a mixture of Syn and anti in acid-catalyzed hydration because we form a carbocation. We have a mixture of Syn and anti in oxymercuration-demercuration because the mercury is going to go on the top for one of the isomers. The mercury can attack first at the bottom, giving us an other. So it looks like it's Syn and anti because it gives us a mixture, but technically it's anti-addition. Technically it's anti-addition, but it gives the products that give us Syn and anti, so that's why it's here. And then if you use an alcohol, you can actually form an ether. And so that's what the alkoxy, which is the alcohol for the demercurization. Okay, now the reactions that only give Syn addition are hydroboration, because we have the hydrogen and boron add across it immediately. We have catalytic hydrogenation, because it has to sit on the surface of the metal. And the Syn Dihydroxylation, because we form the osmate ester on the one side. And then we have the reactions that only give anti. Okay, and that's the halogenation and the hydrohalogenation. So when we want to think about these, we want to look at in these two right here, we form a carbocation. In these two here, it's all about whether the mercury attaches to the top or the bottom first. That gives us our mixture, okay? In the case here, all these Syn additions, we have boron and hydrogen adding across like that. We have our osmate ester forming that interreaction. And then in both of these, we have our halogen forming our halonium cation. So if you put the intermediate of each of these next to each of these reactions, it explains it. You don't have to memorize anything. You just have to remember what the intermediate is. If you remember what the intermediate is, it tells you what the reaction is. All right, let's take a quick break. Smoke him if you got him. No, don't smoke. And we'll take 5 minutes here. Zoom recording. Okay, so now we're going to change gears a little bit. We're going to talk about breaking our double bond, using the activity of our double bond to act as the functional group to change it to other functional groups. So we're not just going to add across the double bond, we're actually going to break the double bond. The first reaction we have for that is called ozonolysis. So ozone is basically an allotrope of oxygen. Most of the oxygen we have is O2, right? And that's what we breathe and like preferably. When lightning strikes, you can form ozone. Okay, it's that weird smell. It's not good for you, so don't smell a lot, but it's got this kind of electric smell to it. So anyway, so what can happen is because ozone is so active, it's reactive, very reactive, it'll add across a double bond in a weird way. And when it does that, it will rearrange and then break that bond with those oxygens. So in the case of ozone, we have two different ways to do the reaction. You start the reaction the same, but there's two different ways to end the reaction. One's called a reducing reaction, meaning you can get aldehydes. The other one is an oxidizing, which means you only get ketones and carboxylic acid. So you have to be attention to what the second reagent is. In this case here, these are the two reagents that give us a reducing environment, meaning we can get aldehydes. Okay. Dimethyl sulfide, because the sulfur wants an oxygen on it, and the zinc metal, and it'll go to zinc oxide. Okay. So these are the only two ways to get to aldehydes. Okay. So what we're going to see here is, in this case here, we have this side substituted twice. So it can only make ketones. Only make ketones. This side has a hydrogen on it. And because we're using one of these two reagents here in the workup, in the second part of the reaction, we can get to aldehydes. So if you look over here, we get a ketone from the one side and an aldehyde from the other. Okay. So this is important because if we used any kind of other reagent in the workup, like water or peroxide or hydroxide, it's going to give you carboxylic acids or ketones. Okay. So how does it work? Well, it's cool because ozone is what we call a dipolar molecule. Okay. It's got a positive and a negative charge. If you look at if you did the formal charge on there, this oxygen's 0, this is +1, and this is -1. Okay, so that means we can do what we call a dipolar addition across the double bond, because we have a positive charge here, which means these electrons want to kick in here, and these electrons want to kick out here to go here and then there. So all three pairs of electrons move at the same time in a concerted reaction to give us our initial heterocycle. What I mean by heterocycle, meaning that it's a cycle, but it has things other than carbon, right? That's oxygen. So it gives this, but that's not very stable. Those oxygen-oxygen bonds are not very stable. So it immediately rearranges to be the ozonide. Okay, now notice this ozonide is also not very stable, but it's more stable than the molozonide. Oh, no. Sounds good. But then by doing a reducing right here, we're going to break this bond. We're going to break this bond, and one of these oxygens is going to go on one of the carbons, one of the oxygens is going to go on the other carbon, and the lone pairs are going to kick in here and give us our double bond between the carbon and the oxygen. Okay, so we're going to form carbonyls, but depending on what the substitution is, we can get aldehydes or ketones with this workup. Okay. It's a really great way to get aldehydes from the system, because what you can do is you can start with a very big molecule with an alkene in it and chop it into smaller pieces. But what if you have a ring? Well, then you're going to open the ring and you're going to have that same number of carbons. Okay. The other way to do this is with permanganate. Okay. Now, notice this is permanganate with heat. Permanganate with heat and water. What it's going to do is it's going to actually take you all the way down to ketones and carboxylic acid. You do not stop the aldehyde because the aldehyde is oxidized by these same conditions. So permanganate with heat gives you that. But I said permanganate dilute cold will give you a diol. You'll add across there, giving you your permanate ester, and it will let you do that. So if it says heat and water, you always go to the carboxylic acids and the ketones. Okay, you do not stop the aldehyde. Now, what happens if you have a terminal alkene? You keep oxidizing that last carbon until it goes to the carboxylic acid, and then the carboxylic acid is carbonic acid, which decomposes into CO2 and water. So you can actually lose just one carbon and get to your ketone on one side, and then this becomes CO2. So we're going to have to do some reactions. We're going to show some examples where you can end up with a ring that has two functional groups on it, or you can lose carbons as CO2. Okay, so let's talk about the rings. Depending on how you work up your reaction, you can end up with carboxylic acids, ketones, or ketones and aldehydes, right? So if we're going to look at that, let's assume we're going to do our ozonolysis on this compound here. This is limonene. It actually smells like lemons and limes. It's actually extracted from citrus fruit. It's what we call a terpene. Terpenes are a class of molecules made by plants and pine trees and stuff like that, but they all have a double bond. Most of them have a lot of rings. Most of them are rings, but a lot of them all have a double bonds. So they have a nice, pleasant smell. Most of them, like pine tree smell, that's a terpene. Okay. So in this case here, we have two double bonds, and we can use our ozone. It's not going to be selective. It's going to hit every double bond you have. So if you have a double bond, it's going to react. And we can split it here and here, right? There. So what happens when we split the one up here? This side is going to give a ketone. We see why. There's already two carbons attached to the carbon with the double bond. So it's going to put an oxygen where that carbon double bond was and give us a ketone. This side is going to give us an aldehyde because we have one carbon and one hydrogen. That's why we learned all the functional groups in chapter 2. So then this side here, we're going to get a ketone on this side. But this is going to turn into an aldehyde, a one carbon aldehyde, okay? Because we're using dimethyl sulfide, a reducing workup. So let's look at our products now. We're going to end up with ketone here, aldehyde, and our aldehyde. But notice our product has lost one carbon. Our big product has lost one carbon because of the terminal alkene. So we need to pay attention to it. And again, this will work with permanganate as well if you heat it. It'll do the same reaction, ozone and that. Oh, actually, it won't do this, will it? Because permanganate will not form aldehydes. It'll oxidize those down to carboxylic acids. So if you want the aldehydes, you have to do ozonolysis. If you want the carboxylic acids, CH3, OH, and CO2 would be the other product here. That's permanganate, potassium permanganate. Right here, we'll give you the carboxylic acids. Ozonolysis will give you the aldehydes. Questions?
They both form ketones.
Yeah, ketone is nice and stable. They will both form ketones. If it's disubstituted, if your alkene is your carbon on that alkene is disubstituted, it'll always form ketones. Okay, it won't oxidize off a carbon. It'll only form the ketone. All right. So let's talk about alkynes. So alkynes do all the same reactions that alkenes do, except you can do them twice. 2 pi bonds twice. So that means if you use one equivalent of bromine, you can stop at the dibromoalkene. And then if you add a second equivalent of something else, you can either get the tetrabromo if you added bromine, but what if you added chlorine? you're gonna get the dibromo-dichloro compound. Or what if you added water? You could get an alcohol, you can do whatever you want there. But if you do it stepwise, you have one equivalent. So to get to the first compound, and the second equivalent to get to the second compound. Now, this is actually kind of cool because what they like to say in this is great atom economy. Because you start with X grams of this and Y grams of this, and your product is X and Y added together. And then you add Z, and so this is X plus Y plus Z. You're not losing anything. There's no byproduct, there's no side product. So it's really good. So if you carefully control this, you can actually get multiple products. Now, in theory, but what if you added one equivalent of bromine? Is it going to stop here? One of these equivalents of bromine can actually attack this. So you're going to end up with a mixture of alkyne, alkene, and alkane. So it's best to just add a second equivalent of the same thing to get to the tetra compound. But this is slightly less reactive, so if you're very careful, you can stop it. All right. So you can do the same thing with hydrohalogenation. Same mechanism, where you're going to add their first equivalent. It's going to give you anti-addition. Just like before, it's going to give us anti-addition. And then your second one is going to give anti-addition, but it follows Markovnikov's rule. Meaning that in the first reaction, when we actually added the halohydrogen, when we did the halogenation of alkene, we got bisenyl dihalides, 1 and 2, carbon 1 and 2, alpha beta. In the case of hydrohalogenation with an alkyne, we can add the geminal dihalide, because as soon as you add a hydrogen, Markovnikov says that we're going to add the hydrogen to that side. So that's the way to get the geminal twin dihalides. So now we have to think in our toolbox here. Oh, I can get bisenyl dihalides from alkenes. I can get geminal dihalides from alkynes. So this is where we're going to prepare you for next semester, in the fact that you're going to start using all these reactions to get selective, more and more selective in the reagents you use. Okay, but it does follow Markovnikov's rule. Okay. Now, the alkynes can be oxidized too, and in ozonolysis, it doesn't stop. It typically oxidizes everything down to carboxylic acid. Okay, so because you can't stop at a ketone. Why? Neither one of those alkyne carbons has 2 carbons attached to it. So it can't stop at a ketone. And it's oxidative enough that it stops at the carboxylic acid. See, there's no second carbon here. It can't stop at a ketone. It only goes to carboxylic acids. Okay. And that works for ozone or permanganate. So that means that if you have an alkyne at the end of a chain, you're going to break that off. This part is going to turn into CO2. And this part is the other half of the molecule is going to be your carboxylic acid. So same reaction, same mechanism, just it happens twice. All right, so this is from the book, okay? This is the page after the one with all the intermediates on it. And we don't do this reaction or that reaction. Those are carbenes. I don't do them, even though they're really cool. I just don't do them because I want you to learn these reactions first. But what we can say here is this is the beginning of our retrosynthesis here. We're starting with an alkene, an alkyne, And we can get to different alkenes, we can do to different alkanes. We can reduce these down and turn into E and Z products depending on which reagent we use. And we can go to carboxylic acids, aldehydes and ketones. So this is kind of the summary of that. And I'm actually going to stop right here. I want to do a whole thing on retrosynthesis tomorrow, because that's going to be our activity is retrosynthesis tomorrow. Okay. So thank you very much. I will see you tomorrow, either live or on film, and we will continue with the